Hi everyone. This is the topic summary video for week 1. In these videos, I'll discuss what I intend to teach you this week, where that will be used, why it's interesting, and some sort of expectation on what you're going to have to be able to do. So there's 4 things that we get through this week. We're going to introduce ordinary differential equations. Some of you may have seen this in school. Maybe a lot of you haven't. You should remember derivatives from at least EM1A. What you're going to see is that an ordinary differential equation is an equation involving derivatives, and your aim is to solve for the function that you've differentiated. There's a lot of different types of ODEs, so you need to know the difference between them. Often we classify ODEs by a means of solution, essentially. So depending on the classification, it depends on how you actually, the method that you use to solve the equation depends on what you've classified the equation as. So it's quite important to classify them correctly. Because you'll have a miserable time if you misclassify the ODE and apply the wrong technique for solution. The other 2 topics are slope fields, sometimes called direction fields, and Euler's method. Slope fields are essentially just a representation of the ODE in graphics form. And the reason that's useful is you can often sketch a solution before you even solve the equation. You can kind of work out simply from the equation what the solution will look like. Now that's very useful for checking your work. You want your solutions to be consistent with everything, so you know if your solution is correct or not. So slope fields are also really easy. They don't rely on any extra techniques other than this sketch of a sketch that is based on information in the equation alone. So it's very straightforward to be able to sketch a slope field, and you can get a lot of information out of it. So a lot of the time you can't solve an ODE, unfortunately. So in the absence of a nice analytic solution where you've got, if you like, complete information about the unknown function, you can still get a lot of information about this unknown function with graphical techniques such as slope fields. The last thing we're going to look at is Euler's method. Now, some of you would have done CPS, computational problem solving, in first semester, where you use numerical techniques to solve problems. Euler's method is the basic numerical technique for solving ordinary differential equations. Given an ODE, you can apply Euler's method to it to approximate the solution of that ODE. Now, as I said, a lot of ODEs don't have nice closed solutions or easy to find solutions. So doing these things numerically becomes quite important in practical situations where you often get a very complicated ODE and you need a simple solution of that ODE. So something like Euler's method, it's a simple means of approximating the solution to that problem. A lot of the other numerical techniques that you'll find in higher level courses, particularly in mechanical engineering, a lot of that it's sort of fundamentally related to the same ideas that you'll see in Euler's method. Why do you need this? ODEs are everywhere. They're particularly in elec. So if you're an electrical engineer, your electrical engineering subjects will be starting to talk about resistance, inductance, capacitance circuits and modeling the behavior of those circuits, so the current and voltage, modeling that circuit response with ordinary differential equations. So that's an immediate link to some electrical engineering, mechanical engineering, and I guess to a lesser extent civil engineering and aero. You're often interested in things with some flexibility, some springiness, and some, I guess, deformation or damping. And all of that deformation and springiness is also modeled with an ODE, or can be modeled with ODEs as well. This all generalizes as well. So ODEs by second year, they'll become partial differential equations or PDEs, and you'll find that that expands all of this stuff out into multiple dimensions and much more practical scenarios. So the deformation of a beam, fluid flow, electric fields, and so on. So all of this is highly fundamental to your later learning. So bear that in mind and enjoy the week of lectures.